Okay, so this is a lot of writing, but we're just going to go through real slowly together. The first rule I need you to write is right here at the top. These are the operations on functions. Let's let f and g be any two functions. Then the sum, f plus g, is the function defined by, and there's two ways to write it. You can write f plus g in parentheses and then an x in parentheses. Or you can write f of x plus g of x. These mean the exact same thing. So if someone says find f plus g, all they really mean is f of x plus g of x. Okay, so for example, let's pick two functions. I'm just going to pick x squared and root x. Okay, so what would f plus g be? It would literally just be x squared plus root x. Not very interesting. Okay, now when I add a function and a function, I end up getting a function, right? So this is a brand new function. I suppose you could even make a flashcard for it if you wanted to, if you feel like memorizing it. What is its domain? Well, look at the expression that we just got, right? Are there any numbers that are forbidden, like x's, that you cannot plug in? Look at the answer. This is my answer. Can you see any numbers that are forbidden? Yeah. Negatives are forbidden, right? So we know that the domain here is going to be x is greater than or equal to 0. So this thing is called the sum function, but it has its own domain, like any other function. Why is the domain greater than or equal to 0? Because this is made up of an f and a g. F will input any number, like you can put any number you want into x squared, but g has a rule. G here is saying, please don't give me a negative number. I can't square root it. So we abide by that, right? So f plus g will abide by any rules that their constituents abide by. So what does f plus g follow? What rules does it follow for domain? Whatever f's rules are and g's rules are combined. Okay? Or actually intersected, technically. Intersected. So let's go on to the next one. So after sum, we can talk about difference. The difference, f minus g, can be written as f minus g in parentheses and then x. Or you can simply think of it as f of x minus g of x. If we were just following along with the same example as before, for f and g, it would look more like this, x squared minus rad x. And the domain would just be, again, x is greater than or equal to 0. Why? Because g is still not accepting negatives. And he's part of our expression. Rad x is still there. Okay, next would be multiplication, right? So we've added f and g, we've subtracted f and g. What happens if we multiply f and g? Well, we call that a what? Not a sum or a difference, but product. So the product f times g, you can write that as f times g in parentheses, and then an x, or you could just think of it as f of x times g of x. In this example we've been working on, f times g would basically just be x squared times rad x. That would be your product function. And the domain is still that we cannot use negatives because that darn rad x.
So we still have the same domain rule here as well. I know it's repetitive, but it's important. Okay? After sum and difference and product, we have the answer to division problem, which is called what? Quotient. Right, so quotient f over g is the following. You can write it as f over g in parentheses and then an x, or think of it as f of x over g of x. And for this one, we have to be a little bit more careful. For example, not only does g have to be defined, but g cannot be 0 either. So this one, we know this rule. You can't divide by 0, right? So we always list this. Anytime you write a fraction like 5 over a, you really should write a is not 0. Here they wrote fx over g of x, so they felt obligated to write g of x is not 0. Let's look at our example, our specific example. For us, f over g would look like x squared over rad x. What's the domain of this one? A little more strict now. We still have that darn rad x. So x cannot be negative, right? So you might think, oh, well, that's just the same answer as last time. But also we have rad x on the bottom, right? So we also cannot let x be 0 just because it would cause an undefined situation also. So basically we have to be a little more strict with x this time. X has to be strictly positive. X cannot be 0 anymore. Or we have division by 0. Not okay. Okay, so there's also a sentence that's written for each one. It says the domain of f plus g consists of all x that are in the domain of f and g. The domain of f minus g consists of all the x's that are in the domain of f and g. The domain of f times g consists of all the x's that are in the domain of f and g. The domain consists of all x's for which g of x is not 0 that are in the domain of both f and g. I don't care so much about the sentences. I care about the notation in black, and I care about the red domains there. Okay? So let's go on and look at some examples of how we might use this, something a little more interesting than what I had. Okay, we'll start off with two functions that are very forgiving. F is just a parabola. Its domain is all real numbers. We can write that as negative infinity, infinity. Or if you don't like that notation, you can just write all real numbers. Or if you don't like that notation, you can write this. It's called a double struck R, and it means all real numbers. I'm going to use the interval notation, negative infinity to infinity. Okay, so I'm going to use this one. Sometimes I use the other one, but for this example, let's use that. What about g? So that thing is just a parabola, right? It's like vertically stretched and it's shifted down forward. But what is this thing? Negative 3x plus 4. It's a line. It's just mx plus b, right? And lines also have domain of all real numbers. The only exception is the vertical line, and that's not a function. So let's get started. Okay, to do f plus g, that means we're going to be adding the function 2x squared minus 4 and negative 3x plus 4. So if we just group our like terms, we notice that these 4's actually cancel out. Okay, the outcome on this problem was it's a parabola. Okay, it's a parabola. So what's the domain? All real numbers. Yeah. You can tell from the expression that you just wrote, 2x squared minus 3x, that any number can be plugged in. There's no denominators, there's no radicals. Okay, let's go to part B, f minus g. Okay, so we have that. So this time it groups a little differently. This time it's this time nothing cancels out. So we get 2x squared plus 3x minus 8. Again, that's just a parabola, a little more complicated. Domain is all real numbers. So things don't usually get very interesting with the first part of these. Like A and B are usually not very interesting. Let's look at part C. F times g of x. That's 2x squared minus 4 times negative 3x plus 4. That's more of a FOIL situation. So if you multiply the firsts, you get negative 6x cubed. If you multiply the lasts, you get 8x squared. If you multiply the inners, you get 12x. If you multiply the lasts, you get negative 16. What's the domain of that thing? Well, there's no radicals, and there's no fractions. So it's all real numbers. And D, F over G. So you're doing 2x squared minus 4 over negative 3x plus 4. So the only thing you have to watch out for here is the denominator should not be 0, because you now do have a fraction. So this is already kind of done. But when you write down the domain, this is a fractional answer. So we just have to make sure that denominator is not 0. So let's set the denominator equal to 0 and solve. Negative 3x plus 4 is equal to 0. Means x equals 4/3 is restricted. So just solve it to find your restricted values. And somebody called this an extraneous root the other day. That's not the right terminology. It's a restricted value or an excluded value. Extraneous root is, you use that phrase when you're talking about solving equations. We're not solving any equations right now. Okay, so what's my domain? Basically, x is not 4/3. Or if you want to write that in interval notation, looks kind of neat. Let's practice that. It's any number from negative infinity to 4/3, or any number from 4/3 to infinity. So if you think about what I just wrote, I basically wrote everything, all numbers except 4/3 is what that means. So you might see that in the back of the book sometimes. But most of those answers came out to like, domain was all real numbers, domain was all real numbers, domain was all real numbers, right? And it's because the two functions that we were given, their domains were all real numbers. Let's do another example. This time, the functions you're given have their own restrictions. Okay, so let's try this problem. And I think I'm going to make this problem a hair more interesting by making this number right here a 3. So here's the problem. F of x is 4 over x minus 2, and g of x is x minus 3 over x plus 1. Actually, let's make it even more interesting. We'll put x minus 2 up here also. So this is a weird function. It's x minus 3 and x minus 2 on top, and x plus 1 on the bottom. Okay, so let's run through this. Before we do anything, we want to write down the domains, because these guys have their own rules, right? F says, don't give me a negative 2. Don't give me a positive 2. I won't take it. And G says, don't give me a negative 1. I don't want it. Okay? So when we start combining these, we want to know that ahead of time. We want to know the rules before we start. So let's write down the domains. This one prohibits x equals 2. And this one prohibits negative 1. They're forbidden values. And they're forbidden no matter what happens in the future. Okay, so let's run through this. So the first one is f plus g. So 4 over x minus 2 plus x minus 3, x minus 2 over x plus 1. Okay, so how do you add fractions? You need a common denominator. Here's a quick and easy way to add fractions. Draw that. What it means is you're going to multiply the 4 with the x plus 1. You're going to multiply the x minus 2 with this chunk. Those will form your numerator. There'll be a plus in the middle. And then the denominator is the product of these two. So this slash means multiply these. This slash means multiply these, and this line means multiply the bottom two. So it looks like this. We're going to multiply the 4 with the x plus 1. We're going to multiply the x minus 2 with the x minus 3 and the x minus 2. So you end up with basically that. And as for the denominator, it's just the product of the two denominators. So that works really nicely when both denominators are primes, like x minus 2 and x plus 1. They're relatively prime. Okay, we can clean up the numerator, but I'm not going to FOIL the denominator. Okay? I like to keep the denominators factored always. So we have 4x plus 4 plus x minus 3 times x squared minus 4x plus 4. And you continue to work this out just to kind of get it cleaned up so it looks like the one in the back of the book, you know. Okay, so we have 4x plus 4 plus, and then we have an x cubed minus a 4x squared plus a 4x minus a 3x squared plus a 12x minus a 12. And group your like terms. So you have an x cubed, looks like you have minus a 7x squared. For x's, it looks like you have 20 x's. And for constants, you have a minus 8. Oops. And the denominator is the product of the two original denominators. Okay, but what's my domain? What's the domain? Yeah. Chase? Right. You can tell what the domain is by looking at your answer, but honestly, we had already said in the outset of this problem that these were forbidden numbers, and they are still forbidden. So you can just go with the original things you wrote down, plus the fact that the answer has an x minus 2 and x plus 1 downstairs. So they're forbidden either way you look at it. Okay, let's go to the difference. Okay, so the difference is just going to be pretty much the same, except there's a few minus signs involved. So I'm going to skip ahead a bit. If you're going to be doing f minus g, I'm not going to redo the whole problem. You're going to have 4x plus 4. This time it's going to be minus x cubed plus 4x squared minus 4x plus 3x squared minus 12x plus 12. So all the signs changed after the first two terms. And this all cleans up, but the domain is the same, isn't it? Look at the denominator. Same exact denominator. Okay, so it looks like this time we lose our 4x's. And we have negative x cubed. For x squareds, we have 7 of them. We have a minus 12x. And for constant, a 16. But look at the domain. That's the most important thing right now. Domain is the same as before. X cannot be 2. X cannot be negative 1. Like I said, they were forbidden from the beginning. They're still forbidden. Let's look at part C. What's f times g? So this is where it gets kind of interesting. Okay, so my functions were 4 over x minus 2, and we're multiplying that with the function what was my function? Can't even remember it now. What was g? It was x minus 3, x minus 2 over x plus 1, right? So x minus 3, x minus 2, x plus 1. So something very interesting happens right now. We'll notice that there's an x minus 2 top and bottom, right? So the naive student would do this. They would say, ooh, cross cancel, which is fine. We need to do that. But they would conclude that the answer is 4x minus 12 over x plus 1. They're right about the answer, but they're going to get the domain wrong. What are they going to put? Look at their answer. They're going to put x cannot be what? Negative 1. Why are they not quite done yet? Because before they canceled out this, they should have written down that x cannot be 2. They lost that information. When this got canceled out, we kind of lost that. And it didn't show up here. There's no x minus 2 on the bottom. But remember what I said. The function f forbade x equals 2 all along. It was never allowed, and it's still not allowed. So you can't tell just from your answer what the domain is. You have to go back to the givens. X equals 2 was never allowed in this problem. Okay? Pretty important. So you can bet on my test I'm going to have a problem like this where there's reduction. You need to write down the domain prior to reducing. You need to say, ooh, x is not 2, and then go cross it out. So do your domain early. I did my domain before I started this problem. Okay, let's look at part D now. F over g. So I have 4 over x minus 2. And then I have x minus 3, x minus 2 over x plus 1. So this is what we call a fraction within a fraction. Not quite a complex fraction, but it's pretty close. Oh, sorry about that. Okay. Pretty ugly stuff. So how many of you had Miss Chen? Okay, so she had a rule where you take these two, the inner ones, and those are your denominator. So oops, sorry about that. The inner is the denominator, and the outers here are your numerator. It's a good rule. It'll just save you some time. So my outers are going to be that 4 times that x plus 1. So that's just 4x plus 4. And the inners, that's the x minus 2 and also the x minus 3 and x minus 2. That becomes your denominator. It is pretty fast. It's faster than that KFC rule where you keep the top fraction, you flip the second fraction, then you cross cancel, right? Inner, denominator, outer, numerator, ID on. Or sometimes she says inner, inner, outer, outer. What would the naive student record as the domain here? They would say x cannot be, look at their answer, they would say x cannot be what? 3. X cannot be what? 2, right? This is their take on it because they're looking at their answer only. They're saying, look, these two guys are forbidden, 3 and 2. They're right, but it's not the full picture. There was a number that was forbidden all along. What was it? Negative 1. It was forbidden at the beginning. It is still forbidden. The reason it's forbidden is right here, prior to the ID on. You can see that negative 1 is forbidden right here. It creates an undefined situation here. After you flip it all around, you kind of forget, oh yeah, that x plus 1 was at the very, very bottom. Okay, so we have to write that down every time. So I guess what I'm saying is your answer contains at least, for domain, the rules that the original functions abided by. So this one has both of the original rules, and there's a new one that popped up. X cannot be 3. Okay. All right, let me just show you something graphically real quick. Let's say you're given a problem like I don't know, just like that first one I did, right? I just want to convince you that this is true graphically. So in the very first example I did, I had chosen x squared, which is this graph. We're all familiar with it. And root x, which is this graph. A little bit hard to see. Let me change the color. Make it black. Okay, they each have their own rules, right? X squared is very forgiving. You can plug any number you want into it. It's mapping out the entire x-axis. For every x, there's a y. The square root function is a little more strict. It says give me numbers that are positive or zero only. Fine. So when I combine these two functions, the stricter one gets to apply the rules. Okay? So, it's kind of like you play Foursquare, right? You guys remember playing Foursquare when you were kids? Let's say that you made a Foursquare version where everybody gets to declare their rules, and you have to abide by all the rules that are stated. Okay? So one person, maybe you guys don't even know what this game is. You guys know what Foursquare is? All right. So it's a game where you bounce a ball, and then each person can have their own rules. So when they get up, they're like, my rules, everybody knows what that means. It's like, oh, okay, so we can't touch the ball twice, you have to do one hand, whatever the rules are for that person. Well, if you have more than one person applying rules, you have to abide by all the rules. That's kind of the idea here. So x squared has no rules, but root x has a rule. So what does the graph of the sum look like, for example? Let's graph it. Let's see what x squared plus square root of x looks like. It has to abide by the rules of both functions. So it has to maintain that x is greater than or equal to 0. Look at the graph in dark blue. X is greater than or equal to 0. It's obeying the rule of the rad x function. Let's try a minus version. So I'll make this a minus instead. There it is, to the right of 0. Nothing at the origin. I mean, nothing on the left at all. It's abiding by the rules of rad x. How about the product? X squared times square root of x. Yep, to the right of the origin. And the quotient, x squared over square root of x. There it is, to the right of the origin. And a little bit hard to see. You can't really tell there's a hole at the origin, but this one actually 0 is forbidden as well. Okay. So all of those obey the rule of the rad x function because that's one of the inputs. Okay, so that's the idea. All right, so we did addition, subtraction, multiplication, division. Is there anything else?
Square.
Powers, that's really an application of multiplication, all right? It's just a subtopic under multiplication. Is there a fifth operation? Let's see, you can take two numbers and add them, subtract them, multiply them, divide them in most cases. Is there anything else? There is with functions. With functions we have composites or composition. Substitution. Substitution. Okay, so I'll briefly touch on substitution today, and then tomorrow will be our domain lesson for that, because it gets kind of tricky. So I wanted to save it for the second day. But if you want to find a composite, that's called F circle G. I like to call it fog. It doesn't mean F times G. It's F of G. It's not the same thing. Okay, so you can write it like this, F-O-G, and then X. The way you saw it written last year was F parentheses G parentheses X, F of G of X. Okay, so maybe this is more familiar to you. But our textbook likes to write it as fog. So what exactly does it mean? It means take G of X and plug it in to every X in F of X. That's what it means. Take G of X and plug it in to every X in F of X. So here's a quick example. Let's say that F of X was the function 1 over X plus square root of X. Sorry about that. lost my page here. Where'd it go? Oh, I dragged it down. Thank you. There it is. All right, sorry. So let's say that you have this function, and g of x, let's just say, is the function x cubed plus x squared, and you wanted to find fog. Fog would have the appearance of f, but it would have g's instead of x's, like this. So instead of being 1 over x, it would be 1 over the function g, plus, and instead of square root of x, it'd be the square root of g. See? That's what fog means. It literally means to substitute. We don't do this with real numbers, but this is a fifth operation with functions. Okay, so what happens is you get these really confusing domain issues, right? Here's what happens. First of all, g is a function of its own, right? So it has its own rules. If you went up to g and said, hey, what's your domain? He'd say, well, don't give me, certain numbers. I won't take it. It's like, okay, fine. So then let's say you give g numbers that it will accept. So like g is like, okay, I'll take those numbers. I can give you outputs. If g outputs a number that f won't take, then we have no business plugging g into f. So I'll say that again. G has its own rules. You can give it numbers, but it might refuse them. Even if it does accept a value, it will crunch out a new value, and that value better be acceptable for f because we're going to go plug it into f. So the output of g must obey the input rules of f. It's confusing. So I'll help you with it tomorrow. I have ways of making it simple. But that's kind of what's going to happen. It's going to be weird. G has its own rules, and its outputs have to obey f's input rules, and ugly stuff. We'll deal with it tomorrow. Today we'll just do real simple stuff here. Let's try one example, and then we'll call it a day. Let's say you have these two functions, 4x squared minus 1 and 4 over x, and you want to find fog of 1. Fog of 1. What does that mean? It means f of g of 1. Well, g of 1 is just a number, right? It's just a number. So let's find out what that is. What is g of 1? What is g of 1? Look at g function. Look at the g rule. What's g of 1? 4, yeah. Okay, so no big deal. This is asking for f of g of 1, but what it really means is what is f of 4? That's all it really means. And now we'll answer that question. It's going to be 4 times 4 squared minus 1. 63. So first we plug 1 into g, then we take the output and put it into f. Let's find GOF of negative 2. So again, that's not g times f, that means g of f of negative 2. So the question you might want to ask first is, what is f of negative 2? And I'm getting 15 because I'm supposed to go 4 times x squared minus 1. So that gives me 15. Okay, so this is really just asking for g of 15, that's all. That's not too threatening. So that gets used as your input for g. So it's 4 over 15 is the answer. Okay, so we just found fog of 1 and GOF of negative 2. I wonder what would happen if we found like fog of negative 2. You know what I mean? So let's try that real quick. Do you think finding f of g of negative 2 is going to give us the same answer as finding g of f of negative 2? Probably not. Probably not. So let's go and try it. It means f of g of negative 2. So we first ask, what is g of negative 2. I'm just getting negative 2. That becomes your input. So this question is asking for f of negative 2. No big deal. That's just 4 times negative 2 squared minus 1, 15. So notice, this is important. F compose g of A is generally not the same thing as g compose f of A. Sometimes these will come out the same, but generally not the same. If they do come out the same, we call those inverse functions. We'll talk about that tomorrow. Okay? It's really important, but it's not important right this minute. Just notice that they come out to different answers. And then the last thing I wanted to find was GOG of, what was it, 1? Let me see. I want to find GOG of negative 1. So what does that mean? GOG of negative 1 means g of negative 1. Well, g of negative 1 is negative 4, so this just becomes your input. And 4 over negative 4 is simply negative 1. And somebody asked a question last period about this particular example. They said, if I do GOG of 10, is it going to come out to 10? Because GOG of negative 1 came out to negative 1. The answer is, in this problem, yes, because 4 over x is its own inverse function. So it doesn't matter if you do GOG of 20, you're going to get 20. GOG of a million is going to come out to 9. But generally, the answer to that question would be no. Okay, so like for example, FOF. If you did FOF of 10, it would not come out to 10. Okay, so anyway, that's all I want to do today. You have about 14, 15 minutes to start in on that problem set. It's not really that hard of problems. Tomorrow will be the weird domain stuff for composition. Sometimes you guys neglect the little question like, what is the domain? That is a huge part of today. So that's not like part B. That's like one of the main focuses. So don't neglect anything from the instructions.